Course. So today is the last lab of this course where we study PID controllers. So does everyone remember in last lab where we studied a lag controller at the end? Can anyone recall what that controller did?
Yes, sir.
What did it do?
So it was a lag controller.
Yeah, that's the name, but what did it do? What was the function?
Reduce steady state error.
Yeah, so we inserted a pole at the origin and that increased the system time by 1. And when we do that, we reduce steady state error or we eliminate it, right, as we have seen. So for PID controllers, we have actually 3 different controllers. We have proportional, which is the P, we have derivative, T, and integral, I. And the function of these controllers is to manipulate the parameters of our response. So by the parameters of our response, I mean things like the overshoot, the rise time, the settling time, and the steady state error. So these are the 4 parameters that we can control with each of these types of controllers. So the 3 controllers, proportional, derivative, and integral. Okay. So I mean, first let's consider a closed loop system. Okay. Here plant means system. Now a PID controller has so if you consider them all together, they have a transfer function like this, which is the Kp, or for the proportional controller, which is multiplied by its gain value Kp. For derivative controller, we do Kd, which is the constant of the controller, and multiplied by S, because if you multiply something by S, that's the same as what?
Derivative.
Yeah, it's the same as derivative. That's why it's called derivative controller. Okay. And for integral controller, we divide by S because that's the same as integration, right? So that's where the 3 names come from, P, I, and D. If we simplify this, we get something like this, right? We divide everything by S. So what actually happens is we put an input into this, summation block, and the output that we get at the end is actually brought back to the input through feedback, and it's subtracted from the input, and we get an error signal. This error signal is passed through our controller. This might be P, I, or D, or any combination of P, I, and D. Okay. And that controller basically, so it finds the derivative of the error, it finds the integration of the error, and it multiplies the error by a constant gain value. Okay. So the function u coming out of the controller is actually equal to the error signal, which is r minus y, multiplied by a proportional term, an integral term, or the integration of the error, and the derivative of the error. Okay. So this is what we get when our error signal passes through our controller. Right, we get error multiplied by a constant value, we get integration of error multiplied by another constant value, and we get the derivative of the error multiplied by another constant value. This is in the time domain. Everyone understand how we got this?
Yes, sir.
No. So this, this is used to compute the new output, right? And the error is then again calculated, and this process keeps going on and on. By when the controller takes the new error and then finds its derivative and integral again and again, something like that. So this is a continuous process. And the thing I was saying, so we can have any combination of P, I, and D in this controller block. We can have P controller by itself. We can have D controller by itself. We can have I controller by itself. We can have PI, we can have PD, or we can have PID, right? We can have any combination. Okay, so what do these controllers do actually? Okay, so if you look at this table, it gives you a basic idea of what each controller does. So KP, or the proportional controller, will reduce the rise time and will reduce the steady state error, right? So those are the positives. But it also increases the overshoot. So that's a bad thing. And it does not change the settling time. Okay, next, an integral controller it will increase the overshoot. So that's immediately a bad thing, increase the settling time. So what are we doing? We're increasing overshoot and we're increasing the settling time. So the time it takes for the response to settle on its final value. But the advantage of the integral controller is that it will eliminate steady state error. Okay, it will completely eliminate any steady state error that our system might have. That's why we want to use it. And if you look at KD controller, we can see that it reduces overshoot and it reduces settling time. So right here, you can see that if you use KI controller, right, you'll eliminate steady state error, but your overshoot and settling time will increase. So to compensate for that, we can also use a derivative controller, right? Because then our overshoot and settling time will not, it won't increase as it does with the integral controller, right? If we use a combination, then we can compensate for the increase in overshoot and settling time and also have no steady state error. Does that make sense?
So is this only applicable for a step input?
At the moment, yes, it's only applicable for step input.
Yes.
So, why do you think KI eliminates steady state error? Can anyone answer?
Because step input has 1 by s, and in the same way KI eliminates 1 by s by cutting the s on both the sides, probably.
No. So what is happening is it's performing integration, right?
Yes.
Yeah. So what happens when we integrate something? We increase the system type by 1, right? If we had, t, it will become t squared, right?
Yes, sir.
And what happens when we increase system type by 1? Do you remember when we had, first order system, second order system, and third order system? If we went from first order to second order, what happened to the error? It changed from a finite value to 0, right?
Yes, sir.
So whenever we increase our system type, our steady state error is either decreased or eliminated. Most of the time it's eliminated. It depends on what type of input you put, obviously. But for step input, anything over a first order system will have in 0 steady state error when we increase the system type, right?
Yes, sir.
That's what happens in that case. But what I want to mean is, if you use, for example, KP and KI together, what will happen? Someone give me a brief description. So we're using KP controller and KI controller together, right? If we implement them together, what will happen? What will happen with the rise time?
So it will be eliminated.
It won't be eliminated, but it will decrease significantly, right? Because both of the controllers decrease the rise time. What will happen to the overshoot? It will increase significantly, right? Because both of these controllers increase the overshoot. And settling time will also increase slightly, but steady state error will be 0. So whenever we have a KI controller, you will know that you'll have no steady state error in your system at all. Okay. So when you use different combinations of these controllers, you can have different effects on these 4 parameters. Does everyone understand that?
Yes, sir.
Okay. So these won't be 100% accurate all the time, okay, because it does depend on the value of KP, KI, and KD. But this is sort of, you can use it as a guide because it will work in most of the cases, unless you have like really different values of KP, KI, KD. So just take this as a guide. Okay. So let's look at an example problem. We have a simple mass spring and damper problem here, right? I think this is very familiar to you from your control system theory course. So how do we model the system? We put F equals to what? The force is equal to what? Haven't you solved this type of system? It was in chapter 2, right?
So ms
Sir,
square
ms square plus
Yeah,
kx plus b.
bx plus k, right?
Bx plus k, actually.
Yeah. So yeah, so your transfer function will be xs divided by fs equals to 1 divided by ms square plus bs plus k, right?
Yes, sir.
So let's assume m equals to 1 kilogram, b equals to 10, and k equals to 20, and f equals to 1 Newton. So we have defined our, transfer function, right? Now let's see what type of, response we get when we apply step input to this transfer function. Okay, so we have our numerator and we have a denominator. I don't think I need to explain this anymore, right? So we just apply step input. Let's see what type of output we get. Okay, what should be the final value of our response? Ideally,
So 1.
1, right? Because we applied step input. Let's check our final value in this case. So if we go to steady state, so this is how we check the different parameters, right? Does everyone know this? We right click on the graph, we go to characteristics, peak response gives you overshoot, settling time gives you the settling time, rise time gives you the rise time. So what's our final value? Our final value is 0.05, right?
Yes, sir.
So how much steady state error do we have? Our input value is 1 and our final value of our output is 0.05. What's our steady state error in this case?
So 0.95.
95%, right?
Yes,
If
sir.
we consider percentages. So that's really a huge amount of error, right? Let's look at our, settling time is 1.6 seconds and rise time is 0.89 seconds or 0.9 almost. So we have a huge amount of steady state error. We have a pretty high values of our rise time and settling time. And we also, but one thing is we don't have any overshoot, right? So that's one good thing from this curve. But the other parameters are pretty poor. So I guess we can change some of these using our, controllers that we have learned so far. But before that, let's insert a feedback into the system and see if that affects anything. Okay, so we're just inserting a negative feedback with single gain, and we're going to see if that affects the system at all. Okay, so you know this code, right, from lab 4?
Yes, sir.
Yeah, so I'm not going to explain it again. Okay. Has anything changed really? What's our final value now? Our final value is, it's even less than before, right? Before it was 0.05, now it's 0.0476. So our steady state error has actually increased more from before, right? Our settling time is same. Our rise time is also the same. It's decreased a bit, but it's almost the same. So adding a negative feedback hasn't really affected our system that much, right? So closing our loop. So next, let's try to input a proportional controller. So the proportional controller, what do? We have a constant kp that we multiply or that we insert before our transfer function, right? So in this block here, we're just going to insert kp. And this block will be our transfer function that we have. So what are we doing? We're just multiplying our transfer function with the kp term. Any confusions?
No, sir.
Okay. So we're just multiplying our transfer function with the kp term. So what's the only thing that will change? The only thing that will change is our numerator. The numerator will be now kp, right? Let's say we select an arbitrary value of kp of 300, just arbitrarily, randomly. Okay, and let's see what type of output we get. So only our numerator is changing, where we're inserting our kp. Okay, so what has happened here? Let me put all the characteristics on, and someone describe this first. What have we improved?
So steady state error has decreased.
Decreased by how much? Let's see what the final value is. It's almost 0.94, right? So our steady state error has decreased from 95% to around 6%. So that's like a huge improvement, right? What about our rise time and settling time? Has that decreased or increased?
Decreased. Rise time
Decreased.
has decreased.
Yeah, so it was before 0.83, now it's 0.07. And settling time has also decreased, right? From 1.5 to around 0.77. So we have decreased all those things. But what has increased?
Overshoot.
The overshoot has increased, right? So even though we're decreasing those three, our overshoot has increased significantly. So that's the drawback of the proportional controller. So if you recall our table, you see the proportional controller, it will decrease rise time, it will decrease steady state error, but it will increase the overshoot. So that's the drawback associated with using our proportional controller. Okay. So next, let's use a PD controller. So we have our proportional and our derivative term all together. Okay. So if we implement this type of, controller, what will be my numerator now of my overall transfer function? What will I write in the numerator space in MATLAB?
Two terms.
Yeah, what will be the terms? Just in terms of K?
KP and KD.
KD, KP.
KD, KP, right? It will be KD, KP. So that's the only thing that will change. And let's assume our KP is 300 and KD is 10. So we have our numerator, we have our denominator from before, and we have our closed loop system, and we're applying a step input. Okay, let's see what type of response we get. What are we expecting to happen? Can anyone recall what our KD controller does?
So
Reduce overshoot.
will be reduced.
Reduce overshoot, and one more thing, overshoot. It was settling time, right?
Yes, sir.
Yeah, so let's see if those decrease again. Okay, so I think you can see almost immediately the overshoot has decreased, right? Let's check our settling time. So before I think it was 0.8, right? Now it's like 0.3 almost. So both my overshoot and my percentage, settling time is decreased. What about the other parameters? Let's check our rise time. It's the same as before almost. And our steady state error should be the same, and it's the same as before. So our KD controller affects two things only. It affects the overshoot and it affects the settling time. It decreases both these things. Okay. Are we clear?
Yes, sir.
Any questions?
No, sir.
Okay. So next, let's use a PI controller and see what that does. So what's the transfer function of if we have PI? It will be KP plus KI by S, right? And that will be multiplied by our, original transfer function. So we have to manipulate this bit. We'll divide both sides by S in this case. So if we, simplify that, we get something like this, right? But what happens is our denominator has increased in order by 1. So we have multiplied S to our denominator. So in this case, our denominator will also change. So what will be my denominator? I mean in MATLAB.
So MBK0.
MBK0, right? And my numerator will be KP and KI. So as you can see, we have our MBK0 and we have KPKI, and we're assuming KI equals to 70. Remember, at this point, we're just choosing these values randomly, just arbitrarily, and seeing what we get. Okay, so what do we expect to happen? What will change in our curve if we have KPKI?
State error will be 0.
Overshoot.
We have more overshoot, and one thing will be eliminated. What was that?
Steady state error.
Yeah, the steady state error should be eliminated this time. Okay. So let's check our steady state error first of all. Final value is 1. So as expected, we have 0 steady state error, right? One, I mean, parameter is increased significantly. Can anyone tell me what it is other than overshoot?
Settling time.
The settling time, right? So before it was like 0.3 or something, right? If you can recall. Now it's almost, I mean, almost 5 seconds. So if we insert an integral controller, our transient error, so we refer to, the settling time. If it has increased settling time, we say that our transient response will degrade. So if we insert an integral controller, it will take a huge amount of time for our response to settle to the final value. This will be really detrimental, right? We don't want our, output to fluctuate between a lot of values. We want it to settle as quickly as possible. So if we use an integral controller, that's the drawback. That our settling time will increase significantly, and it will take a huge amount of time for our system to settle. Even though we have 0 steady state error, it will take a large amount of time for our system to reach that final value. Okay, and also the overshoot, as you can see, has increased. So those are the two drawbacks. So it's almost 33%. That's a lot of overshoot. Okay, so that's what happens when we insert an integral controller. Any questions? So how do we improve our PI controller? How do we reduce our, rise time and our overshoot? Sorry, settling time and overshoot. While having 0 steady state error.
We introduce decontroller.
We introduce a decontroller. So now we will have our PI decontroller, okay? And it should have the best, overall scenario. So the transfer function is going to be this term multiplied by original function. So what will be my numerator and my denominator? From this equation?
So numerator will be KD, KP, KI, and 0.
Will there be a 0?
Oh, no, sir.
No, sir.
Yeah, just KD, KP, KI, right?
Yes,
But
sir.
my denominator will have a 0 at the end. It'll be
Yes, sir.
MD, K0.
Yes. Yes.
Okay, so we're going to use KP equals to 350, KI equals to 300, and KD equals to 50. Okay, so these values were obtained using many trials and errors. So these are the optimal values. In later sections, we'll use a better method, but for now, we've used a lot of trial and error to find these values. Okay, just assume that. So let's try this code and see what we get. Okay, so how does this response flow? What are the good things? What are the bad things?
The rise time is very low. There is
Estimate is very low.
almost no steady state error.
Yeah, I think 0 steady state error.
Yes.
Final value is 1. And our settling time, what was it before? It was almost 5 seconds, right? Now it's what, 0.83 seconds. So that's improved significantly. And we've eliminated our overshoot as well, right? So what does it mean when we have almost zero rise time? So 0.05. It means so the combination of rise time is settling down. This means our output is almost close to our input from the very initial stages, right? That's what we want. We want our output to match our input completely. That's not going to be possible, but in this case, we're getting really close to the input from right at the beginning, right? So this is a very good thing. And we also have zero steady state error. We have our final value is equivalent to our input value. So when we implement PI and T controller together, we can get this sort of output. Any questions?
No, sir.
So what are the steps for using a PI controller? We obtain an open loop response first of all, and we determine what needs to be improved. Okay, so if you can recall, we looked at our open loop response and we saw that these are the parameters that I need to improve. Now, so we can add a proportional controller to improve the rise time. We can add a derivative controller to improve the overshoot, and we can add an integral controller to eliminate the steady state error. Okay, and we can adjust our Kp, Ki, and Kd values until I obtain a desired overall response. So, for example, say I want an overshoot of less than 5%, right? I'll start with a certain Kd value, see how much overshoot I get with that. Then I can either increase my Kd value or decrease my Kd value if I don't reach that certain percentage that I'm looking for. Does that make sense? So we have to adjust the values of each of these, Kp, Ki, and Kd until we get our desired response in our certain range. So if we want rise time less than 1, we're going to have to change the value of Kp until we get a rise time less than 1. Does that make sense?
Yes, sir.
Okay. So one thing to keep in mind is that you don't need to implement all 3 controllers into a single system. Okay, it's not necessary. So for example, if a PI controller gives a good enough response, then you don't need to implement a derivative controller to the system. We're trying to keep the controllers as simple as possible. Okay. Now we're trying to adjust, Kp, Ki, and Kd each time until we get like our desired output. We can use a loop for that, right? We can insert a loop in our code. So we change our value of Kp, Ki, and Kd each time and see what type of output we get, right? It will be pretty easy if we insert a loop. So that's what we're doing in this code. We have our original MP and K values, and we have an initial value of Kd, Kp, and Ki equals to 100 each. Okay. So what does this line do while 1? Devin?
It will always run the loop.
It will always run the loop, right? Unless we manually break it. So what are we doing in this case? We have our numerator denominator. We're computing a step response for any value of Kd, Kp, and Ki we already have. Okay. And then we check if the system fulfills the design objectives. If it fulfills the design objectives, we press 1, and then our loop will break. If it doesn't fulfill our objectives, we press 0, and we input new values of Kp, Ki, and Kd, and then run the loop again. Then we check again if it fulfills our objectives. We press 1 if it does, we press 0 if it doesn't, we input new values of Kp, Ki, and Kd. So we can continue going like this until we actually get our, the ideal values that we want. So we just implemented a loop to make sure, to do it as quickly as possible. Any questions about this code?
No, sir.
Okay, let's try it out. There is one thing missing in this code. Can anyone tell me what it is? Any ideas?
The closed loop transfer function.
Yeah, we haven't formed the closed loop transfer function, right? We have to do that. So we have to insert that line. So right? So that's the line that was missing. Where did it break? Okay, now let's run our code. So how does a response look? I mean, what's the settling time? Where's my point? So we don't seem to have any silicon error initially because obviously we have our KI controller, right? What's the rise time? It's about 0.0362. Okay. So this is for KD equals 100, KP is 100, KI is 100. Let's say I want to change some values. I would put 0, and then we would enter new values of KP. Let's say 350, 50, and 200. And then we can see what changes we get. So as you can see, our curve changed significantly. So you can play around with those values and until you get, your desired overshoot, rise time, settling time, etc. Any questions? Do I need to explain it anymore?
No, sir.
So that MATLAB part is done. The next part is associated with Simulink. So everyone please, start with Simulink because you'll have a task with Simulink later on. Okay, so we're going to build the model of the given system. So the spring mass system that we had previously, we're going to implement this transfer function or the model using Simulink. So what is this block called? Can anyone recall that we input our spring damper system into?
LTI system.
LTI system, right? So okay, that's cool. And we are going to use a block called PID controller to, that will obviously do the controlling stuff. And we have a step response as previously. So let's build the system first of all. Okay, it's similar. So we have our step input. So we need our step input first of all. We need our summing block. We need our LTI, LTI block. We need our PID controller. and we need a scope. Okay. Should be remember there should be plus and minus, okay? Because we're subtracting down. To change that to minus. What's our transfer function? Can anyone tell me? Numerator is 1. What's the denominator? 1. What's our spring damper system transfer function?
10 means
1, 10, and 20. Okay, so after you have built your model, go double click on your PID box. Okay. You're going to see, you have your initial value of P, I, and D. These are just there from the beginning. Okay, and there's a button called Tune next to your select tuning method. Click on that, and it will take you to another window. Okay, so
So
using
it's
this,
a flat line, sir.
sorry,
So the output.
yeah, we haven't run it yet. Just don't run it. Just go to your PID block and then double click it and select Tune. Okay, it will take you to another window. We're going to look at that now. So everyone should get this type of window when you click Tune. Okay. So here, what you can do is you can interactively select, what type of response you want. So on the top, you'll see 2 bars, one for response time and one for transient behavior. You can use the slider to, select what type of response you want. If you want it to be faster in response time, your rise time will decrease a lot. If you want the transient behavior to be more robust, it will, decrease the overshoot and stuff like that. If you want it to be aggressive, it will have a lot of overshoot. So things like that. You can interactively change your, type of response. And if you click on the show parameters window, it will show you what, your P. So this is the initial values of P, I, and D you have in your block, 1, 1, and 0. And these are the new values that you need to get this sort of response, okay? So for example, if I make it more robust, look, my P value, my I value, and D value are changing accordingly. Okay, so you don't need to, manually keep changing the values of KP, K, and KD. You can just come to this window and you can select what type of response you want by looking at the rise time, the settling time, the overshoot. When it gets to your specified level, so I say I want less than 5% overshoot. Now it's less than 5%. Now I'll have my PI and TN values that I need, get that sort of, parameters, and then I can just hit update block, and all the parameters here will be transferred to my block. Okay, so we can easily select our PI and D values as required by the system. Any questions?
so what is capital N?
Capital N is called the filter coefficient, and you don't need to worry about that one. Just focus on the PI and T values.
Yes, sir, clear.
Clear? So everyone's going to try this out, okay, for a different transfer function. So if you're clear, then what I want you to do is build this model in Simulink, okay, and I'll give you another transfer function to input here. Then you go to your tuning window and get a good response. I mean, by tuning your response, and then show me the P, I, and T values. Everyone clear on the task?
Can you repeat again?
Yeah, so I'll give you a new transfer function, which you input here. I mean, you change this block, the values. Then you go to your PID window, you click on tune. You come to this window, you'll, I mean, get a good response by changing these around. Then you show me the P, I, and D values. The new ones, that is. So,
Sir, I have a question, sir.
yeah.
Sir, we don't need to change the initial control parameters of the PID controllers, right? So
What
we
do you
just
mean by that? You mean, first of all, it's 1, 0, those things.
yes, sir, the default ones.
No, you don't need to change it. You just click on tune, and when you, I mean, move this around, and then you can just click update block, and it will transfer those parameters to your block. Okay, so
Okay, sir.
when you double click it now, it will show you these values.
Yes, sir.
Okay, so I want screenshots of your block diagram, and I want a screenshot of your tuning window where I can see your, I mean, your tuned response and your original response. So this, right? And also your parameters. So take a screenshot of this and then upload it to Google Classroom. Okay?
Sir,
Yeah.
is it possible to submit this later?
It will take like 10 minutes, right? Why do you want to submit later?
Oh, sir, my internet connection is not working. So I can't download any lab report or I can't upload anything. I am doing class with my mobile.
What's your ID?
80.
Okay, you can submit it later then.
Okay, sir.
What time do you want to submit it?
Sir, I have also some issue.
Yeah.
My electricity has gone, so I can't access MATLAB right now.
Okay, how many people don't have access to MATLAB right now? Or can't submit right now?
Sir, ID 53.
53 and 80. Anyone else? Okay, I hope everyone else has, been working. So then I can give you use this transfer function for your, I mean, the new transfer function. I want you to do the tuning for this transfer function. Okay. So everyone other than ID 53 and 80, use this transfer function and build your Simulink model, then tune your output to some specified, I mean, range that you can figure out for yourself. You don't need to, there's no right answer, just select any that you think is good. Okay.